Hello, my name is Samuel Schleifer, and this is my Physics 2212 Lab 4 on magnetic braking using Faraday's law. Introduction to this lab. The purpose of this lab was to explore Faraday's law, which relates changing magnetic fields to induced electric fields that drive currents. Specifically, the lab investigates the interaction between a falling bar magnet and a conductive tube made from aluminum foil. So we made the computational model using GlowScript. The system here is just the bar magnet and the aluminum foil tube, and then the surroundings are everything else. Some fundamental concepts behind this lab. First and foremost, we have Faraday's law, which just states that the electromotive force is equal to the negative derivative of the integral of the magnetic field times the normal vector times the derivative of the area. And then the Biot-Savart law, which just states that the magnetic field is equal to mu naught divided by 4 pi times the current times a very small change in distance in the wire, cross product with the position vector divided by the magnitude of that position vector squared. And then finally, this fundamental concept is magnetic flux, which just states that the flux is equal to the integral of the magnetic field times the normal vector times the derivative of the area of the surface that the field is pushing through. For the procedure, we assumed three things. One, air resistance is neglected. Two, the bar magnet acts as a perfect magnetic dipole with the north side facing up. And then the only forces acting on the system are magnetic and gravitational. On the left, you see a picture kind of our setup where we drop the magnet through this tube. The eddy current is shown using the blue moment, and then the green arrow shows the magnetic motion. Here are the experimental results. So we had 5 trials on the right, and you can see the time it took the magnet to fall through the tube for each trial. The average time at the end was around 0.76 seconds. So some properties for the magnet. The mass was around 0.025 kilograms, and the dipole moment was 4.613 amps times meter squared. For the experimental data, like I said, there were 5 trials with an average fall time of 0.76 seconds, but the time in free fall from the same distance without being in the tube was 0.43 seconds, showing that there's a very significant change due to the magnetic force. This was the GlowScript code. In the top, you see the code used to compute the magnetic field. On the left, you see the code used to compute Newton's second law, and on the right, you see the magnetic flux. And this was the results of the computational model. So you can see at the start, gravity is the driving force, and there's a big dip down in velocity. And then everywhere where the graph is linear, just a horizontal flat line, is where the force of gravity is equal to the force of the magnetic vector, giving us a net force of 0. And then at the end, gravity takes over again. These are 3 questions in the lab. Which color corresponds to clockwise/counterclockwise current? Based on Lenz's law, red indicates counterclockwise current and blue represents a clockwise current. What happens if you flip the magnet? The magnet will still fall the same way. The components change a few signs, but the overall result is the same. How does real world change in time compared to the computational? So the simulated time is slightly shorter due to ideal conditions. Obviously, in the real world, there's things like human error and air resistance. And then what does the plot shape tell about forces acting on the magnet? So gravity dominates whenever the magnet enters and exits the tube, but gravity and magnetic force balance when it is inside the tube. So some potential errors. First and foremost is friction. The magnet could be hitting the sides of the tube, which would have a big impact on the amount of time it takes to fall through it. Some measurements. The stopwatch may or may not have been stopped and started at correct times just due to human error. And then in the real world, there's air resistance we decided to not account for in our computational model. Some discussion questions. What if the tube's resistivity were close to 0? So with very low resistivity, Ohm's law, which states that voltage or change in voltage equals the current times the resistivity, tells us that induced current would increase. So this would create a stronger opposing magnetic field, which would cause the magnet to fall even more slowly. And then what if slots were cut into the tube? So if slots were cut into the tube, it would break up the ring currents, which would weaken the opposing magnetic field, and then as a result, the magnet would fall faster through the tube because force of gravity would be more of a driving force.